So I will give you a short update on performance work that we have been doing. As Andre mentioned, from an HPE perspective, we are supporting Slingshot, of course, InfiniBand and Ethernet. From a community side, we also still work with Cornelis networks, and we are hoping that they will eventually continue their work to expand the OPX provider so we can use OPX with Cornelis. But TCP works. And as we mentioned in Stefan's talk, MTU size essentially determines what you can get on the Cornelis side. In this talk, I will focus about InfiniBand and Slingshot. So the first thing I wanted to just recapture here, I think we presented that in an earlier session, is that with InfiniBand, by default, when you're using the verbs provider, you're using reliable connections. And DAOS being a user space communication interface, there are a lot of connections that you have to establish. The slide here, I don't want to run through all the numbers, but essentially all MPI tasks from your job have to contact all targets on the servers. And if you do the numbers, this is for the LRZ system, which isn't huge. It's 42 servers and 250 clients roughly. You can count the number of queue pairs that you need. For 8 SSDs per system, 4 per engine, you get numbers here where on the server side you're already approaching 100,000 queue pairs with 1 target per disk. And there is a hardware limit actually on the ConnectX adapters of 128K queue pairs. If you want more metadata performance, usually you want more than 1 target per disk. And if you just go to the 24 targets that we're running right now at LRZ, the number of queue pairs that the server would need to hold is 645,000, which is far exceeding hardware resources. So it's very clear that with these user space mechanisms where you don't have a daemon on the client side and you really connect to all the targets, you have like 2 orders of magnitude more connections. There's no way you can do that with RC. It took us over a year essentially to finally go to all the different combinations of what we could use. On an InfiniBand fabric, we switched to UCX, and then you have the availability of both the DC mode, dynamically connected mode, and also UD. We had to fix a number of bugs both on the UCX side and on our side, and eventually we ended up using UCX with the DCX provider, and that allows us to share queue pairs and actually scale to the number of like logical connections that we need. And I'm summarizing in the chart here the evolution of the performance of this InfiniBand system at LRZ. We have the numbers from SC'25, which are the bold black ones, right, where we could run to roughly 6,500 client tasks on the 42 servers. With the submission that we just made, we achieved an improvement of roughly 38% by switching from libfabric to UCX and then being able to almost triple the number of client tasks. So we'll have to wait until Thursday for the absolute numbers, right? But on the same hardware, we can now increase the number of client tasks to actually running 1 MPI task per physical core on all of the servers. So that's a great result, but it's taken roughly a year really to weed out all the details. Andre presented the hardware design of the K3000 servers that we will productize from the HPE perspective. And a lot of work on our side has been spent on determining the performance metrics essentially of like what is the impact of the number of drives in the system and what is the impact of number of CPU cores on the servers. And Andre already walked through the details of the hardware configuration. We can essentially go from 8 drives to 20 drives, and we can go from 1 target per drive to like as many physical cores as we can have on the server. And I have a bunch of slides here, and I will just flip through them in the presentation. You will have that in the backup, and you can read them in your own leisure. Those charts on the left-hand side show the single server with 8 NVMe disks, and on the right-hand side they show the single server with 20 NVMe disks. And then the different graphs in those charts show an increase of the number of targets per disk from, in this case on the left-hand side, 4 targets on 4 disks up to 32 targets on 4 disks. The x-axis is the total number of MPI tasks, so number of nodes times number of tasks per node. And then we're going through the different performance metrics. You can see on the left-hand side here, this is an 8 NVMe disk system. IOR easy write is limited by the disk bandwidth, whereas on the right-hand side with 20 drives, you can reach essentially the 2 times NDR bandwidth of the single server. This is all single server SX, no data protection. And I'll just flip through those here to show you some of the effects. For reads, of course, as Andre mentioned, with 8 drives, we can already saturate the read bandwidth of the server. So left and right-hand side essentially look the same. This is IOR easy. You also see that adding targets doesn't give you anything for IOR easy, right? A single target per disk can maximize the disk for sequential IO. This is different when you look at the IOR write, hard write and hard read, which are like finer granular. Here you see an actual increase from 1 target to 2 targets to 4 targets, and very little effect here going from 16 to 32 targets per disk. So this is again the IOR hard scenario, where on the left-hand side we're limited by the number of drives. For reads, same picture. As you add targets, you are able to achieve more IOR hard performance on the same number of drives. And again, left-hand side is a little bottlenecked by the total number of NVMe disks. One thing that we were all very interested in is the IOR random 4K reads that the IO 500 committee just introduced shows a very similar behavior here, right? As we increase the number of targets, the number of like physical CPU cores that we dedicate on the server side, we can increase the random 4K read IOPS to essentially, in this case here, over 3 million IOPS on a 2-socket server. Those curves will go up a little bit more, but not too much. We only had like 16 nodes of 32 cores right now for this test here, but we have done other studies that go slightly higher. These results, among others, have also like led us to using 48-core CPUs in the server, because that really gives us the maximum of what we can squeeze out of the storage hardware in those systems. All right, switching from InfiniBand to Slingshot. First of all, I want to call out a paper that our colleague Jerome, together with Argonne and DAOS core team, have presented and published at DUG this year. This is available free access right now. I have the link in the slides here. Because on Aurora, there have been a lot of activities optimizing the RPC path, right, to get to that scale. Of course, Aurora Slingshot doesn't use Q pairs, so you don't have that blow up in Q pair scales that you have on InfiniBand, but certainly at the Aurora scale, there's other issues that you have to address, and they did a great write-up of all the improvements that have been going into DAOS. As Andre mentioned, we did some early investigations on the Slingshot 400 system. And in this case, those are using single socket servers. So we're definitely not limited. Although the K3000 will be using dual socket systems, this experiment has all been done with the DL320, single socket, 4 NVMe disks and a single Slingshot interface. This is all pre-GA work. So firmware and Slingshot host stack still under evolution. And we have been able to saturate, from an IOR easy perspective, the system, like the hardware bandwidth of the disks. In this case, the different colored charts here are not target numbers, but those have been 8 servers, so we were able to run data protection in addition to just SX. So there's an SX graph, there's an erasure coding 4+1 and an erasure coding 4+2 here. And you can see as you increase the number of tasks, we're able to reach like 360 gigabytes per second on read, which is roughly the hardware bandwidth. And on writes, because this is only 4 NVMe disks per engine, essentially the same as the left-hand charts for the InfiniBand part. The limit here is roughly 178, and we could get a little closer. It's like 80+%, not 95% as for the reads, but we're pretty happy with this level of the maturity of the Slingshot 400 right now. And same picture for the random 4K reads. As you would expect for a read workload, you're getting the same performance for SX and 1 or 2 parity erasure coding. And on this system, we're reaching roughly 2.5 million IOPS. That is certainly something that we are still looking into, because those are 32 drives. The results that I showed on InfiniBand were with only 20 drives, and we were getting 3 million myopes. So there's still some performance to be gained here, but overall, for a system where like the host software stack and everything is still in flight, we are happy with the results. I didn't include all the metadata testing results here because there's like 6 or 7 different IO500 metadata tests, but results are so far pretty consistent. One thing that we also still need to work on is the IOR hard on Slingshot. There are some issues there that we're still looking into. We're not able to scale as high as we can on the InfiniBand side. So that's work to do on our side, but I think it's still a bit of time before Slingshot 400 will be officially released. All right, and that's all I have. Questions?
Multiple sockets?
No, this system had DAOS servers with a single socket CPU and a single Slingshot NIC. The clients actually had 2 NICs because those were like two socket AMD systems with a lot of cores. So on that system, we have been running 128 MPI tasks per client. Yes. And that just happened to be the platform that was used for this. This is a cluster in manufacturing that we're using for Slingshot 400 validation. Actually, for that and for the DL360 Gen 12, there also will be an IO500 submission. So watch Thursday, and you will have all the numbers. I just wanted to show the scaling graphs here because it's really important for us to understand where do we max out the system and where does it make sense to spend money, essentially, right? And where does it stop to throw more hardware at it.
When you use a logarithmic scale, it makes the curve of the graph less intuitive in terms of the model and the equation.
Sure.
Because you get an inflection point that should be.
That's true, yes. But we still want to do log because we want to scale out long enough, right? Otherwise, you're focusing too much on the long tail. Okay.
Thank you, Marco.
Thanks.